We start with a northward perspective of Detroit, extending lines from the central business district and creating a grid with longitudes and latitudes placed every 4 miles to form squares of 16 square miles. Given the township survey and layout of state roads in Michigan, this pattern is convenient for further subdivision. We highlight the CBD coordinates in red and place markers on these lines at 17 miles from the CBD. Using this Cartesian plane, we locate other points of the same radial distance at points on the grid. We identify them by setting 17 miles squared equal to the sum of longitude miles squared and latitude miles squared. Next, we add the ancient primary paths known today as Michigan, Grand River, Woodward, Mound Road, and Gratiot Avenues. We locate coordinates for a secondary ring at a radial distance of 32 miles. Let's reduce the brightness of the principal radial paths and extend the grid in the southeast. We also extend the Woodward path into Windsor, Ontario, Canada. Then we draw the southwest path known as the Toledo Road. Building our model, we add vertical density axes at the CBD and at the points along the radial paths intersecting with the subcenter rings. With these axes, we can measure the density of land values, population, or building height. Depending on the density to be measured, we scale them to appropriate units. Wishing to vary the relative height of these vertical lines, we mark the CBD as the tallest with an index value of 1. For the first ring of subcenters, let's reduce the height index of the vertical axes to 50%, while decreasing this index at the outer ring subcenters to 25%. Next, we add density curves between local maximum points. With actual data, these curves can be estimated using U-shaped quadratic and asymptotic negative exponential functions. These functions can be integrated both radially and laterally. Using similar lines, the secondary lateral curves are wider and lower than the first. Finally, we complete our topological surface of densities by taking the double integral of the sum of all functions combined. This combination of topological algebra and integral calculus produces a density surface that resembles the sheeting of a circus tent. Our system remains flexible by allowing us to add or delete subcenter axes, vary their height, and otherwise alter our model as desired.